Hello friends, I am Dr. Gaurav. In this video, I will discuss about reverse Carnot Vapour compression cycle. Contents are reverse Carnot Vapour compression cycle. Impracticalities associated with reverse Carnot Vapour compression cycle. So first is reverse Carnot Vapour compression cycle. The Carnot cycle is totally reversible cycle, therefore all the processes that comprise it can be reversed, in which case it becomes the reverse Carnot cycle. It has the maximum coefficient of performance, that is COP, for given temperature limits, and it serves as a standard cycle against which vapor compression cycles can be compared. Carnot refrigerator and Carnot heat pump works on reverse Carnot cycle. Reverse Carnot vapor compression cycle is composed of four reversible processes as shown in figure. So this is the schematic of reverse Carnot vapor compression cycle, and this is the TS diagram of reverse Carnot vapor compression cycle. We can see here we are having four components. First is compressor, second is condenser, third is turbine, fourth is evaporator. Four reversible processes are discussed below. Reversible adiabatic compression or isentropic compression, process 1-2. Temperature rises from TL to TH. You can see here process 1-2. In this process the component is compressor. So refrigerant, which is our working substance, will enter the compressor where it gets compressed and become point number 2. So there is isentropic compression. You can see here we are having isentropic compression from 1 to 2. And there is increase in temperature. The temperature at point 1 is TL and temperature at point 2 is TH. So there is increase in temperature from 1 to 2. And the compression is such a way that our refrigerant will become dry saturated vapor at point 2. We know that in case of isentropic process, heat transfer is 0. Next process is reversible isothermal compression, that is process 2-3. TH constant, that is temperature is constant, T2 equal to T3 equal to TH. You can see the point number 2 will enter the condenser, and surrounding the condenser there is a warm medium at temperature TH. So when this refrigerant enters the condenser, it will lose its heat to the warm medium at TH, and it will become point number 3, which is saturated liquid refrigerant. So here the refrigerant is losing its latent heat of condensation to the warm medium at TH. So we know that amount of heat supplied to high temperature reservoir at TH for constant temperature process is given as QH equal to P2 V2 natural log V2 upon V3, or we can say M RG TH natural log V2 upon V3, where P is pressure, V is volume, M is mass, RG is gas constant, TH is temperature of high temperature reservoir. Reversible adiabatic expansion or isentropic expansion, process 3-4. Temperature drop from TH to TL. So you can see the refrigerant at point 3 enters the turbine where expansion takes place, and this expansion process is isentropic expansion. You can see in the TH diagram 3 to 4 there is temperature drop from TH, because TH equal to T2 equal to T3 to TL, and TL equal to T1 equal to T4. So there is a temperature drop as well as there is a pressure drop from 3 to 4. So this is isentropic expansion process. And we know that heat transfer in case of isentropic process is 0. So process 1, 2 and 3, 4 are just opposite of each other. Next process is reversible isothermal expansion, process 4.1. Here the temperature TL is constant, that is T4 equal to T1 equal to TL. Amount of heat removed from the low temperature reservoir. You can see from 4 to 1 the component is evaporator. Now refrigerant at point 4 enters the evaporator, in which we are having a cold medium at temperature TL. Now this cold medium will give its heat to the refrigerant at point 4, due to which the condition of refrigerant will become point 1. This one. So in this case refrigerant is absorbing equal amount of heat, and now this point 1 again enters the compressor, we get the point 2 and the cycle continues. One more thing you can see here, the reverse Carnot cycle operates in the counterclockwise direction. You can see the direction is counterclockwise, 1, 2, 3, 4. The direction is counterclockwise. So every counterclockwise cycle is a work consuming cycle. Always remember this. So for process 4.1, the formula will be, because it is a isothermal expansion process, so we will say QL will be equal to P4 V4 natural log V1 upon V4 equal to mRg TL natural log V1 upon V4. As process 1-2 is isentropic compression, so we can use the relation between temperature and volume as T2 upon T1 is equal to TH upon TL is equal to V2 upon V1 whole raised to power gamma minus 1. As process 3-4 is isentropic expansion, so we will get T3 upon T4 is equal to TH upon TL is equal to V3 upon V4 whole raised to power gamma minus 1. Comparing the above two equations, we get, if we compare these two equations, we get V2 by V1 is equal to V3 upon V4 is equal to, or we can say V2 upon V3 is equal to V1 upon V4. So you can see V2 upon V3 is equal to V1 upon V4. So V2 upon V3 is equal to V1 upon V4. So we can say QL, this is the value of QL, and here we are having V1 upon V4. So V1 upon V4 is equal to V2 upon V3. So QL will be equal to P4 V4 natural log V2 upon V3. We have replaced this V1 upon V4 with V2 upon V3, or in terms of mass mRg TL natural log V2 upon V3. For Carnot refrigerator, the formula of coefficient of performance is output upon input. So our output in case of refrigerator is this cold medium, because we want cooling. So in case of cooling, this QL will be our output and the input will be work supply to the compressor. So QL divided by W net in, work in, and the value will be QH minus QL. W net will be QH minus QL and output is QL. So this ratio will give the COP value. If you put the value of QL and put the value of QH, you will get this relation. Cancelling the common term, you will get TL divided by TH minus TL. That is lower temperature divided by higher temperature minus lower temperature. Always remember in this way. For Carnot heat pump, the value of the COP will be, in case of heat pump, our output is heating. So our output in this case is QH. So output upon input, QH divided by W net in, QH divided by QH minus QL. Putting the value of QH and QL, you get this relation. Cancelling the common term, we will get TH divided by TH minus TL. High temperature divided by high temperature minus lower temperature. Hence, COP of Carnot refrigerator and heat pump is independent of the working fluid, that is refrigerant. It only depends on the temperature of source and sink. Both COPs increase as the difference between the two temperatures decreases, that is as TL rise or TH fall. So when TL rise, the COP increase, or when TH falls, the COP decrease. COP increase. Now, impracticalities associated with reverse Carnot Vapour compression cycle. First is all the four processes have to be reversible. It is impossible to perform a frictionless process. So all the process 1, 2, 3, 2, 3, 3, 4 and 4, 1 must be reversible. Practically it is impossible to have all the processes as reversible process. The heat absorption and rejection take place with infinitesimally small temperature difference. It is impossible to transfer the heat without temperature potential. So there is no temperature potential, you can see here and here. So there is need of temperature potential. Isothermal process can be achieved only if the piston moves very slowly to allow heat transfer so that temperature remains constant. So if you want to achieve this isothermal process, that is from 2, 3 and 4, 4, 1, then you have to move the piston very slowly. It can be achieved in this way. Adiabatic process can be achieved only if the piston moves as fast as possible so that heat transfer is negligible due to very short time available. So the process 1, 2 and 3, 4 must be very fast to achieve the isentropic process. The isothermal and adiabatic process take place during the same stroke. Therefore, the piston has to move very slowly for part of the stroke and it has to be moved very fast during the remaining stroke. This variation of motion of the piston during the same stroke is not possible. Process 1, 2 and 3, 4 cannot be approximately closed in practice. This is because process 1, 2 involves the compression of liquid vapor mixture. You can see process 1, 2. Point 1 is wet point, that is mixture of liquid and vapor. So what we are saying, process 1, 2 and 3, 4 cannot be approximated closely in practice. This is because process 1, 2 involves the compression of liquid vapor mixture, which required a compressor that will handle two phase, and the process T3 involves the expansion of high moisture refrigerant in a turbine. Because of this, problem could be eliminated by executing the reverse Carnot cycle outside the saturation region. But in this case, we have difficulty in maintaining isothermal condition during the heat absorption and heat rejection processes. So what we are saying that process 1, 2, in this point 1 is wet point, it is liquid vapor mixture. So if the entering of the refrigerant in the compressor is liquid vapor mixture, then the compressor will feel some problem, so we have to increase the size of the compressor to deal with liquid vapor mixture. Similarly, for 3, 4, 0.4 is having dryness fraction value very less. That means it is having more value of moisture content in it. So when it exits the turbine, there are chances that the turbine blade will get eroded. So to remove these difficulties, we have to move this point 1 towards right here. So, or we have to remove the moisture content. We have to make this point 1 dry saturated. When we do this, then the point 2 will be here. So point 2 and 3 will not have the constant temperature. So this 2, 3 process will not be a isothermal process if you move this point 1 towards right. So this is the problem with reverse Carnot cycle. Therefore, we conclude that reverse Carnot cycle cannot be approximated in actual practice and is not a realistic model for refrigeration cycles. However, the reverse Carnot cycle can serve as a standard against which the actual refrigeration cycles are compared. These are the references used in the video. Thanks. Any questions you can write to me gaurav.citem@gmail.com.